we all see air pollution constantly all around us, and perhaps some point of time it causes us to wonder, why are we so dependent upon carbon to satisfy all our energy needs? Well, what I'll do today is I'll try to give some sort of a technical insight into why we are so hinged upon and stuck with carbon, and if there could be a cleaner and better way forward. So again, to return to the idea of air pollution, well, within the Indian context, we know of it very well, simply because every winter, all our cities get draped in thick layers of smog, smoke, haze, whatever we call it. Most of this is actually particulate matter, and it gives rise to all kinds of allergies. We even have the cases of pollution holidays being declared, simply to ease off the situation out there. What this really comprises of, to a good measure, is soot, and this originates, of course, from combustion of hydrocarbons or other carbon-based fuels. The other major pollutant which we are familiar with, and perhaps more familiar with, is carbon dioxide. Carbon dioxide is something which does not act locally and give us a large amount of haze, but rather it acts on a global scale, causing catastrophes of devastating magnitude. It causes climate change, which has given rise to floods in Uttarakhand, Kerala. It has also given rise to receding rainfall patterns in Cherrapunji, and those are, of course, a few examples taken from all over the world. The catastrophe is there everywhere to see. Now, we know that there is a move to constantly move away from messier and dirtier carbon fuels, such as biomass and coal, towards cleaner ones, which range from, say, natural gas to, in some cases, we might even call petrol that. But really, that brings out a question. Why are we so hinged on carbon? Why is carbon always there? To play the devil's advocate here, quite frankly, we are not short of elements. One would think, looking at this fragment of the periodic table, which I'm putting up here, that there's really no shortage of things which are out there. We could always, are we just being lazy by not picking up another element? As it turns out, in practice, our choices get far more limited. It's a lot harder to do this than we think it is. And what I'll try to do is, I'll try to go over why it's so hard. To really shed a deeper light into this question, we have to ask ourselves a few other questions. The first one of them being, what really do we do with energy and how do we use it? Now, over here I'm showing how the commercial sector uses energy. This is not intended to be a number per se, but rather an indicator of what things happen. And as you see, I've divided the energy consumption into two parts. Firstly, there's transport, and secondly, I'm just calling it others. Now, why would I do that? Why do I want it to be these two divisions? We find that around a third of the energy consumption goes into transport and 2/3 into others. And the real reason to do that will become obvious in a few slides to come. Firstly, the main difference between these two applications is when we are talking about transport, we are talking about moving consumers, meaning the energy source must move around, perhaps, along with the person who's consuming it. This counts things like vehicles, airplanes, and so on and so forth. On the other hand, when we are dealing with immobile consumers, we are consuming energy at one point. And there's always this option which opens up that we can actually use this energy or obtain this energy simply by hooking up that application to the electrical grid, or else in some other way, maybe power it by renewable electricity coming from, say, a local source. Now, you might think that in many cases this is not true. It is, after all, very, very inconvenient to, say, cook with electricity or use use electricity entirely for cooking. Certainly, we do have preferences towards natural gas, even when we have electricity available. The real reason why I'm making this division is the following. At the end of the day, even though we have a inclination to use natural gas, say, for cooking, it's not like the options aren't there. We have microwaves, we have electric stoves, and so on and so forth. It's just a matter that we find them inconvenient as of now. But as I'll try to show you, perhaps the situation might change. Now, as things stand, there are, of course, I've made these two divisions, but in truth, there are some exceptions to both these rules. For example, there are industrial processes like smelting, which is extraction of metals. And over there, it's unlikely that we'll eliminate our carbon dependence because carbon is not just a source of energy, it actually is a chemical which goes into that process. Secondly, there are, of course, moving things like electric trains, which while they are vehicles and they are moving around, they actually are hooked up on the grid. They actually do use electricity and therefore work in a totally different way. But that said, this division by and large works for the story I am about to tell. And that is the following. If we think of everything we can hook up to electricity, there's a very good reason why we would want to cheer for it and be happy about it. As things stand, India is already generating around 35% of its electricity entirely from renewable resources. This, if we think about it, is a pretty massive number. If we think of an economy like US, that's around 17%. So 35% is very, very good. And this is hydro, sun, wind, so on and so forth. The really, really great thing, however, is that at least by government projections as of now, we are supposed to increase our renewable basket by another 220%. If that turns out to happen, in that case, within 2 years or a little more than that, we would have almost 50% of our electricity coming from renewable resources. The great news is this is going to be pretty cheap because a lot of renewables are, once set up, they just, like the name suggests, are very easy to run and therefore get cheaper with time. What that means is we might have a lot of electricity to go around, and therefore there'll be a strong motivation to connect whatever we can on the grid to the grid. But that said, the problem of vehicles would return. What exactly do you put into the fuel tank? Because a vehicle needs a portable or carries its own portable source of energy. Right now, there are, of course, technological possibilities that we might have vehicles running also connected to some kind of grid, but that sounds very, very impractical as of now, even though it's possible, but almost impossible as well. So what goes into the tank? Well, to answer that question, we have to ask a slightly different and maybe an unanticipated question. We first ask ourselves a very naive question. What really is chemistry all about? Firstly, why do I ask such a question? The reason is we are putting a chemical in the fuel tank, and then we have to figure out why we don't want to put it in there. Well, that's a silly question. We all know chemistry is about chemicals. Well, chemicals are molecules, or made up of molecules to a good measure. Molecules are made up of atoms and so on and so forth. Atoms themselves, if I divide further, contain particles like protons, neutrons, and electrons. I won't go any further because that is where I want to end. What chemistry is all about, chemistry is a way of counting electrons or seeing what the electrons are doing. But atoms are more interesting than that. It's the protons and neutrons which actually carry all the mass in the atom. Electrons are relatively lighter. They of course have mass, but they don't contribute in that big a way to mass. But the deal with atoms is also that most of the stable ones contain nearly equal numbers, almost equal numbers of protons, neutrons, and electrons, give or take a few here and there. What that ends up meaning now for us is chemistry now is a science of electrons, so it's less concerned about what the protons and neutrons are doing, but rather the electrons. But not just that. Chemistry concerns itself mainly with what the outermost electrons are doing. So for most of the atoms, this means we have something called a valence shell of electrons, which is what participates. And even most pathological cases, we are talking about the most energetic 8 or so electrons. In the less pathological cases, 4 or fewer electrons, which actually participate and give us all the chemistry that we do. And that means that's where all our fuels also derive energy from. It's only around 4 or so electrons in every fuel, in every atom of the fuel. So what does that mean, really? It means that when we pick an element of the periodic table, for the most part, once we go outside of this number, all the other electrons are in for the ride. Now, we may not care about the electrons that much, but they bring along the protons and the neutrons as well. And what that ends up meaning is we are just picking up a lot of mass while having very few electrons doing all the work for us. Where does that take us? To take a very practical example, let's consider lead. It's not even shown on this table. It's way down in the periodic table, but the deal with lead is it's already there in all our vehicles. It's already there in all the cars. It's what starts your car off. It's in the lead acid battery. Now the great thing is, if we consider making an electric car, we can't really do it by taking all our lead acid batteries and stacking them, 10 of them together and trying to turn on the car. The reason is because if you put 10 of them within your car, most likely if you have anything reasonable, the car will probably collapse in its own weight. The thing you might try is, well, let's take a heavier vehicle, maybe a tank or a truck, put them in there. You'll find that the lead acid battery, okay, might start up the engine, but it's not going to propel or take things very, very far, simply because it does not have the energy content to actually propel itself. It's too massive. What that teaches us is we have to pick off elements from the lighter side of the periodic table. Of course, the lightest element is hydrogen, and we wouldn't be wrong in looking at it first up. Hydrogen is certainly a fantastic source of energy. It contains a very large amount of energy, which is around 140 megajoules per kilogram, which is way higher than what, say, even something like petroleum contains. That's really, really great. And people did think of hydrogen, and there was talk of a hydrogen economy. But the problem with hydrogen is that it starts off by being a gas, which means it's very, very voluminous. So while it wins hands down when we are talking about per kilogram, when we talk about per liter, it's several thousands of times less energy dense than petrol, which means at the end of the day, if we are talking about what hydrogen would do, well, if our car looks something like this little vehicle which is on one side, Well, hydrogen-powered cars would sort of, if they have to go the same distance, would look a lot larger. They would have that huge fuel tank behind. It would look rather ridiculous. It would, of course, be very impractical, not to mention extremely unsafe to drive around in. So at the end of the day, well, people thought about compressing hydrogen and a few other tricks which I'll come to, but by and large, hydrogen sort of fails on us. We must therefore look further and maybe drawing inspiration from that, not look at gases per se, but rather liquid and solid elements. Well, the next up is helium. Helium is not reactive. We can't do that. Lithium. Lithium is now something which checks a lot of boxes. Lithium is a solid. It's a wonderful material, and it's already out there in the new generation of electric vehicles, where it's used as a lithium-ion battery. It's also there in all our cell phones and so on. The great thing about lithium is it works. It is able to make batteries, which actually do a great job. The problem, of course, is lithium is around 1/10 as energetic as petrol. So, well, that's good to make a car, but perhaps not great. So, not all cars and not all applications could be covered by that. The second problem which lithium faces is it is rarer than many other elements. And therefore, we'll find that its prices will keep shooting up as time passes. We must therefore move on and hope that we find something else. Well, we look to beryllium, we find it's too toxic. Before we jump off this, sort of divide in the periodic table, well, I need to say one more thing about hydrogen and bring it right back. And when we say that the economy today is a carbon economy, that's truth but not part of the truth, because we realize what we use are actually hydrocarbons. Now, what is the deal there? Hydro actually stands for hydrogen, which means what is carbon doing? Well, carbon is acting as a carrier of hydrogen. Hydrogen binds, hydrogen atoms are bound or reacted with carbon, and it is that what we put into our fuel tanks. In that sense, carbon behaves as a carrier atom, in some sense carrying hydrogen. So it's, in a very twisted sort of a sense, hydrogen was always there in our economy. The rest of the elements which we have to the right will have to be considered in that light. They'll have to be thought of as hydrogen carriers. Well, the first step is boron. People tried boron really hard, but then the problem is boron itself has toxicity, and that, as well as a few other things, limited its ability. Carbon is the problem. Nitrogen, well, nitrogen is a nice gas which is all around in our atmosphere, but the trouble is as soon as you start thinking of nitrogen and you try to burn nitrogen hydrogen compounds, you realize you'll make nitrogen oxides as well, and they are extremely toxic. They actually cause acid rain. Certainly not something we want to try. Oxygen is already there around us. It's part of combustion anyway. Fluorine, well, fluorine is so toxic it becomes a hazard when you are dealing with a few parts per million. They create trouble. Moving onwards, neon again doesn't do anything much for us. We move to sodium. Once again, we hit a jackpot. Sodium is an element which is used to make batteries, but sadly we realize sodium-ion batteries are so heavy right now, they can't really propel vehicles. In other words, the periodic table is over, right? Because if we go any further, we find elements and more and more massive, and our story sort of sadly stops. What that means is what we are left with are essentially simply two elements, which we sort of singled out. One is lithium, the other is our problem element, carbon. And that's where everything ends. We will, in some sense, be stuck with carbon. We can always pray that lithium will take on more and more of our applications, but in some way or the other, carbon still is likely to remain the element somewhere. So what can we do? Are we stuck with smoky skies forever? Well, not really. There are a few things which we can do and are still being done. One of the major ones is to still keep shifting towards even cleaner fuels. The cleanest of them all, one of the cleanest of them all at least, is methanol. Methanol is something which, of course, our country is investing greatly in already. And the idea there is methanol is a fuel which is around half as good as petroleum. But the great thing about methanol is it does not produce any soot at all. It's incapable almost of producing soot. And what that ends up meaning is that, well, at least our haze and particulate matter would go down. The second deal, which is an exciting thing on the horizon, is perhaps the idea of artificial photosynthesis and solar fuels. The idea there is actually to use solar energy or sunlight directly to drive chemical reactions similar to photosynthesis, similar to what plants do, but rather than doing it with a leaf, do it with a semiconductor. The idea being, or the hope being, that one can do it with a far greater efficiency and perhaps actually reverse all the damage which we have done. This is still an idea in the works. There has been great success recently in this effort, but it's still an ongoing process, and we hope that something good turns around on this front. So what would our future look like? Well, one hopes certainly that we would see more and more renewable energy showing up. That itself will help us clear up the skies quite a bit. And we also hope that some process like artificial photosynthesis or a solar fuel making method will come in and scrub our carbon dioxide back into where it belongs. So that's all I had. Thank you for your attention.